Today's topic is second order effects. There are three second order effects. One is body effect, second is channel length modulation effect, and the third is sub-threshold conduction. So these are the second order effects. So we will discuss first, that is the body effect. Generally, body terminal of transistor is connected to the source terminal and it is connected to the ground. Okay, now if body terminal is not connected to the ground, if it is connected to the negative supply, that is negative voltage, that is less than 0, then in that case, see what happen. So when you connect this body terminal, or we can say substrate terminal of the transistor to the negative voltage, so holes which are present here due to the p type of substrate will attract towards this terminal, because this is negatively charged terminal, so holes will attract towards the negative voltage, so it will leave here negative ions. Okay, so due to which charges in a depletion region increases and it will affect on a threshold voltage of a transistor. So when you connect this body terminal to the negative voltage, holes which are present in this region will attract towards the body terminal, they will leave negative ions, so that will increase charges in a depletion region, and due to which the threshold voltage of transistor is increases. So when body voltage will decrease, it will increase charges in a depletion region, which will increase the VTH. So VTH is equal to VTH 0 plus gamma, that is body effect coefficient, in a square root of 2 pi f plus source to body voltage minus square root of 2 pi f. So this is a body effect. Generally this body terminal is connected to the source. Source is grounded here. We apply the voltage on gate, that is a positively voltage. This is a NMOS, so we apply positive voltage on gate. Drain terminal is connected to the positive supply and body voltage is less than 0, means negative. So due to the negative body voltage, holes are attracted towards the negative terminal of this body, or we can say substrate, so it will leave the negative ions here, and that will increase the charges in a depletion region, and due to which it will affect on VTH. VTH is increases, and this is the VTH value when you consider the body effect. So this is the VTH without body effect, and when you consider the body effect, this is the equation for VTH, it is increases. So this is a body effect coefficient. Second, channel length modulation. Now see a channel length modulation. Suppose source is grounded, we apply the positive voltage on gate, and VDS1 is the voltage initially applied. Okay, now when you apply positive voltage on a gate, source is a supplier which will provide electrons, and that electrons will travel towards the drain through this channel, or this is the medium. So electrons are moving from source to drain via channel, and ID current start to flow in a MOSFET. So initially, see, this is the length of the channel from source to drain. Electrons are moving from source to drain through the channel, and this is the length of the channel. So for VDS1 you will get the maximum length of the channel. When you increase the VDS1 to VDS2, so in this case second diagram, VDS2 is a greater than VDS1. It means when you increase drain to source voltage, at that time length of the channel is decreases, and that is called as a channel length modulation effect. When you increase drain to source voltage, the length of the channel is move from source towards the drain. So length of the channel is decreases. If you compare these two diagrams, in a first case length of the channel is the maximum for VDS1, and when VDS2 is greater than VDS1, in that case the length of the channel is small. So length of the channel decreases when you increase drain to source voltage, and that is called as a channel length modulation effect. So it is given by the equation ID. So ID in a saturation region is equal to 1 by 2 mu n C ox W by L VGS minus VTH bracket square. This is the equation of ID in a saturation region without channel length modulation effect. When you consider the channel length modulation effect, you can add 1 plus lambda VDS. VDS is a drain to source voltage and lambda is a channel length modulation coefficient. So ID is equal to 1 by 2 mu n C ox W by L VGS minus VTH bracket square 1 plus lambda VDS. So this is the equation of drain current in a saturation region when you consider a channel length modulation effect. Next second order effect is a sub-threshold conduction. So basically how transistor is work, when you apply a proper voltage on a gate, in case of NMOS, when you apply a positive voltage on a gate, so due to which channel is created. So when you apply the positive voltage on a gate, and that is equal to threshold value VTH, so channel is created and electrons are moving from source to drain. In that case current start to flow. When you increase voltage on gate, so more number of electrons will attract towards the drain, and that will increase the ID. So ID is increases when you increase the VGS. So as soon as when you stop a VGS voltage and when you make that VGS voltage is equal to 0, so transistor should be a turn off, but this is not a practical case. When you make VGS 0, there is some current that is flowing to the transistor, and that is called as a sub-threshold conduction. So when gate to source voltage is dropped below some threshold value, MOSFET will not turn off. So there is some weak inversion layer is exist, and due to which current is flow from drain to source. So for VGS is equal to less than VTH, ID having some finite value, and we will give the equation of ID like this. ID is equal to I0 exponential VGS zeta VT. So zeta is greater than 1, that is a non-ideality factor. Vt is kT by Q. So when VGS is less than VTH, transistor ID current is not immediately 0. It will start to decrease in an exponential manner, and that is given by this equation. ID is equal to I0 exponential VGS divided by zeta into Vt. So this is called as a sub-threshold conduction. When you make VGS is less than VTH, in a transistor there is some weak inversion layer exists, and that will due to which current is flowing from drain to source having some finite value, and this is given by the equation of ID is equal to I0 exponential VGS divided by zeta into Vt. So these are the three second order effect. Body effect due to which VTH is increases, channel length modulation, the length of the channel is decreases when you increase the VDS, that is a drain to source voltage. Sub-threshold conduction, when VGS is less than VTH, there is some still weak inversion layer is there, and due to which there is a finite drain current from drain to source, and that is called as a sub-threshold conduction. So these are the three second order effect. Next point, that is a MOS device capacitance. So every two terminal of transistor having a capacitor. For example, the capacitor between gate and drain is a CGD. So capacitor between drain and substrate is a CDB, that is a body. Capacitor between source and body, that is a CSP. Capacitor between gate and source, that is a CGS. So every two terminals of a transistor having a capacitance. So capacitance between source to drain is a negligible. We can neglect the capacitor between drain and source. So this is a gate terminal of a MOSFET, this is the drain, this one is a source and body terminal. Next point is a small signal model. So when we apply a small AC signal for a transistor to amplify that signal, so for that AC signal, how transistor is react, how we can represent a small signal model for that transistor, so we can calculate a voltage gain equation for the amplifier. So basically gain, voltage gain is equal to output voltage divided by the input voltage. In that case you should know for that particular amplifier what is the voltage gain equation. In that case we need a small signal amplifier. So first we will see how to draw a small signal model for a transistor. So ID is a function of VGS because gate to source voltage will control the length of the channel and due to which the drain current is controlled. So when you increase the gate to source voltage, more number of electrons are moving from source to drain in case of NMOS, and due to which ID will increases. So IDs depend on VGS. So we can draw a current source that is depends upon the voltage. So this is a voltage dependent current source and this value is equal to GM into VGS. So this is a basic small signal model, a gate terminal, drain terminal and source. This is the voltage between gate and source. ID, drain current, is represented by a voltage dependent current source, that is GM into VGS. ID is equal to GM into VGS because transconductance is equal to change in ID with respect to VGS. Transconductance GM is equal to ID divided by VGS. So from this equation ID is equal to GM into VGS. So this is a basic small signal model. Second point, due to channel length modulation, when you increase the drain to source voltage, it will affect on the length of the channel. So that is represented by a current source that is depends on voltage. Okay, and that value is alpha VDS. Okay, a current source that is depends on, whose value depends on voltage between drain to source. Now see, R0 is equal to output resistance of transistor is equal to by Ohm's law V by I. V is the voltage between drain to source and I is the drain current. So we can rearrange the terms like this: 1 upon change in ID with respect to change in VDS. ID equation is this one, that is 1 by 2 mu n C ox W by L VGS minus VTH bracket square 1 plus lambda VDS. So you can differentiate ID with respect to VDS, you will get this equation. Okay, differentiation of drain current in a saturation region with a channel length modulation effect. So when you differentiate ID equation with respect to VDS, you will get that 1 by 2 mu n C ox W by L VGS minus VTH bracket square lambda. So this part of the equation is a ID in a saturation, so we can represent this part as a ID. So R0 is equal to 1 upon lambda ID. So we can represent output resistance R0 and whose value is equal to 1 upon lambda ID. R0 is equal to 1 upon lambda ID. When you have to consider the body effect, you can represent it body effect by a current source that is voltage dependent current source, and that is equal to GMB into VBS, that is VBS is body to source voltage. So body effect is represented by a voltage dependent current source, and that is equal to GMB into VBS. So this is a small signal model when you consider the body effect. So GMB, that is a change in ID with respect to body to source voltage. So see, this is the equation, that is mu n C ox W by L VGS minus VTH minus derivative of VTH with respect to body to source. So this is the equation of VTH with a body effect. You can differentiate this VTH with respect to body to source volt. So derivative of VTH with respect to body to source voltage is equal to minus derivative of VTH with respect to source to body voltage. So we can differentiate this equation. So we will get that minus alpha by 2 into 2 phi f plus VSB square root of this. So GMB is equal to a transconductance alpha divided by 2 square root of 2 phi f plus VSB. So this is the eta. So GMB is equal to eta into GM. So we can draw a complete small signal model for the transistor, that is the small signal model with a capacitor between two terminals. So ID is represented by voltage dependent current source. This is the output resistance of transistor R0, that is equal to 1 upon lambda ID. This is the current source due to the body effect, that is a voltage dependent current source GMB into VBS. A capacitor between gate and drain, capacitor between gate and body, capacitor between source and body, and capacitor between drain and body. So this is a complete small signal model for a transistor you can use for the NMOS.